Yes. So last time I proved for you that the space RPN, n-dimensional real projective space, it is a manifold with dimension n, and it is not orientable if n is even. This I was able to prove completely, and if you remember, the main point was that well, there is a sort of standard atlas, and very standard atlas, which is considered usually in algebraic geometry, has n+1 charts, and the domains of the charts of every of them is Rn, just whole space, so they are, as I say, connected. But the intersections are disconnected. And we observed that if n is even, then the two charts, well, I considered some charts, but actually any two of those, not any two, the charts which I considered. Well, the intersection is disconnected, I say, and the transition map has positive Jacobian on one of the components of the intersection and negative on the other one, which contradicts, as we observed, contradicts completely to orientability. A manifold which has two connected charts, so that the transition function within their intersection doesn't have constant sign, somewhere positive, somewhere negative. Such a manifold cannot be orientable by very simple lemmas. Now I want to add to this that if n is odd, then RPN is orientable. Let me give you a short proof. So, my theorem, yes? Oh, excuse me. I didn't do the most important thing. Orientable or not, it is, after all, secondary importance. This? Yes. So let me return to this thing of secondary importance. RPN, and n is odd. It will be important at some moment, not immediately. I'm going to prove that it is orientable. For this purpose, I consider charts. Charts are, let me write, p sub I, Rn in Rpn, and it takes the point x1, xn into x1, xi minus, no, here I need to write colons, xi minus 1, 1, xi, xn. This is the definition of a chart. Now, let us take two charts, number I and j. I suppose that I is greater than j. They're different, definitely. Then, I take this point. I apply phi I, and I get x1, xi minus 1, 1, xi, xn, according to this formula, which I will have to erase maybe at some moment. Then I want to apply to this phi j inverse, but it will be convenient for me if the item number j is 1. So I say that this is equal to x1 over xj, xi minus 1 over xj, 1 over xj, xi, xn over xj. Certainly this is defined if xj is not equal to 0. And then, well, I said to you that I will have to erase it. And then I apply to this phi j inverse, and I get, again, a point of Rn. And here, actually, the coordinate number j. So I write xj minus 1 over xj. Xi minus over x. No, everything is wrong because I is greater than j. So let me write it again. J is somewhere here. So this goes to x j minus 1 over xj, then xj plus 1 over xj, then so on, then xi minus 1 over xj, 1 over xj, and the last one xn over xj. So here now, from this to this is my transition map. It is defined on Rn where xj is not 0. If xj is 0, then it's not defined. Now, let me apply my limited skill in calculus and try to write the Jacobian matrix for that. First, so what's the Jacobian matrix? I take this and I take derivatives over x1, x2, and so on and so on. When I take the derivative with respect to x1, I get this and zeros. I will write it. And this, then the second row will have 1 over xj in the second place, right? And so on. So I will have this part of it is this. Then certainly this is the most difficult thing. I need to take the derivative with respect to xj. And you know, so this will be x1 minus x1 over xj squared up to minus xj minus 1 over xj squared. Then next thing, minus xj plus 1 over xj squared, right? This is the column number j. And so on, minus xi minus 1 over xj squared, then minus 1 over xj squared, x minus xi over xj squared, and so on, minus xn over xj squared. If something is wrong, then please forgive me. But even if it is wrong, definitely all the rest will be okay. Because I need to take derivative with respect to xi plus 1 and so on. Next row will be 1 minus 1 over xj and zeros here and zeros otherwise. And actually so on up to some moment. And then when I reach this, so I take the derivative over, no, it is here. So, and the last one will be minus 1 over xj squared, xj res, yes. So this is maybe not, because this should be also diagonal. This is the Jacobian matrix. Now probably you are able to compute the derivative of this, the determinant of this. For this purpose, it's very convenient to take this row, and this row has the number j plus 1, and to move it in such a way that this goes to the diagonal. And this will be between I minus 1 and I. So I take this row and move it here. Right? What do you think the price of that? -1 to the power of the number of rows in between, right? This number is certainly I minus j minus 1. I hope you believe. The number of rows between these two positions. So the whole determinant will be this. And now the only entry which will be, the only term in the determinant which will not 0 will be the product of diagonal entries, which is as usual minus, because of this minus, x j to the power n plus 1. This is the formula which we get. Now, what do you think about the sign of this? At this moment, probably, it's very important that n is odd. Because if it's so, then the last factor does not affect the sign. It's positive. We have only -1s. So this determinant, -1 to the power I minus j because of this. And the determinant is greater than 0 if and less than 0 otherwise. So far it is correct. You probably teach calculus, work in calculus rooms, so you probably can do it perfectly well. But this result, still it doesn't satisfy us fully. We need to say something. I prefer to say that all the transition maps have positive Jacobians. And then orientable so on. But with this greater than 0 and less than 0, I don't have this. And I need to say one more thing. So we have an atlas. Let me write Rn phi1, Rn phi2, Rn phi3, Rn phi4, Rn phi n plus 1. And the odd numbered charts are compatible, are compatible. The even numbered charts are compatible between each other, but odd and even are not compatible because of that. By this reason, I reflect all the charts which are even numbered. If you really prefer, you can reflect the odd numbered charts, but not all of them. As soon as I do this, then this, so you understand what happens here. I first reflect Rn in a hyperplane, and then apply the same phi. And now all the charts are compatible. And we have our result, that Rpn is orientable if and only if and only if the dimension is odd. Rp1, you may know what Rp1 is, but we will discuss it separately. Semi the circle, oriented. Rp2, projective plane. This is a textbook example of a non-orientable manifold. Rp3 also has something important about it. We will discuss it later, but it is orientable definitely, and so on. So this was my first observation for today. There is a problem in my problem list to determine orientability or non-orientability for Grassmann manifolds. I recommend this problem absolutely. It is a good problem. you will be interested in it. Okay? Now next thing. Well, next thing if you don't have questions. So this is done. Example, fully investigated, what is orientable, what is not orientable, and so if you don't have questions, then I want to say that something could disappoint you in my story, and I want to actually say something to amend this disappointment. I said a manual, very abstract definition. Not everybody likes abstract definitions, especially if we have a course more or less in geometry. Then examples. Some people think, I'm not one of them, but some people think that examples clarify the definition. It may be not so, but we had examples. Rn is a good example, too trivial for us. Spheres, well, projective space, certainly Grassmann manifolds. But what is really disappointing here, that we move very slowly. That to obtain a new example, we need to have a definition of some set and atlas and everything. So, for example, we have 4 examples. Suppose we want to have 6 examples, and each requires some work. And for lazy people, not like you, but it is like me, it is certainly not a good option. So let me say that there are constructions in differential topology which provide many examples in just one click. To begin with, I will consider important but not the most powerful construction. 2 of them. First, suppose we have 2 manifolds, x and y, right? Of some dimensions, maybe different, maybe the same. Then it's possible to form a direct product. So we have x, we have y, and we have atlases for both. And atlases. Here u alpha, phi alpha, and here v beta, psi beta. Then you consider the product x cross y. It is a product of sets, and I believe you know what it is. If you really want to pretend that you don't know, I can say that set of all pairs, a point of x, a point element of x, element of y. And now it is very possible to arrange an atlas for this. Namely, to take u alpha times v beta. It is an open set where this is in space, say, Rn, this is in the space Rm, this will be in the space Rn plus m. Phi alpha, phi psi beta. It's a map which takes a pair of this and the point here and here into their images with respect to phi alpha and psi beta. So this is a chart, obviously, and I will not even check this, but it is really true that this charts form an atlas which satisfies all possible conditions. By the way, in topology, I mean what you call point set topology, there's also a notion of a direct product. Well, for algebraists, which we cannot tolerate here, it is a categorical notion. Direct products exist in many categories, even coproducts. Well, I didn't say this. But there is such a thing as product topological spaces. You know that a manifold becomes a topological space. And certainly this product of manifolds will be also product in the topological sense. That is, topology in x cross y will be the product topologies in x and y. This gives you at least some amount of new examples. For example, you can take products of spheres, right? Not necessarily 2. You can take several spheres, 5. And this operation of product in some natural sense is associative. So we can take product of several, finitely many. Manifolds, if we don't want to consider infinite dimensional manifolds, which we don't do. It is actually the infinite dimensional case in the manifold theory is not very clear. There are different approaches, different definitions. Yes, so this sort of gives us a lot of new examples. A lot means what? Not too many, not too few. Some amount of new examples. If nothing, if you don't want to say anything else about this, I will give you an equally useless construction, one more construction. Questions about the products? You? Questions about the products? Next construction, open sets. If you have a manifold, well, it has topology, then any open set and this manifold is also a manifold with respect to the same metals, more or less. And if you don't insist, I will not say anything else. By the way, orientability, I again want to have your learned opinion. First, the product. What about the orientability of a product? What do you think about that? When is this orientable?
Both the spaces are orientable. It's definitely orientable.
Yes. I can say that the golden rule of arithmetic, that minus times minus is plus, doesn't work here. Because a product of a non-orientable manifold and any other manifold is not orientable. So a product is orientable if and only if both of them are orientable. And something can be said about orientations. What about open sets? What is the relation between orientability of a manifold and its open set in this manifold regarded as a manifold also?
The original could be non-orientable and the open set orientable.
You begin with something sad, and I prefer to be more optimistic. If X is orientable, then every open set is orientable, which can be formulated in a more dramatic way. If a manifold has a non-orientable open set, then it is not non-orientable itself. But it is true that a non-orientable manifold can have very much orientable open subsets. Just take any chart. It will be orientable. So this also gives you some new examples. Just to make it more funny, I can say something about this. You see, among our examples, Euclidean spaces, and we can regard as an Euclidean space the set of matrices, say n cross n matrices. They form a Euclidean space with dimension n squared. What about matrices whose, say, determinant is not equal to 0? How do you call them? Non-singular matrices. This is an open set in the set of all matrices, right? But it's a very important set. It has even a notation. I will give a course in Lie theory. When? Winter, yes. Then I will now I don't want to say the notation to you, but still no secrets from friends. GL and R, 4 letters. GL are two capital letters, which means general linear. Then in parentheses N, which means that just the dimension of the space, and R, our usual R, G, L, and R. It is a Lie group, also a manifold. So this example is sort of good, but not too much. And now let me give you a construction, if I am allowed to call it so, which actually give a lot of examples of manifolds in some sense, which maybe I even will be able to clarify today. It gives all possible manifolds. And this is a notion of a submanifold. And here I want to have again your learned opinion about what a submanifold is. So first of all, we have some n-dimensional manifold. Some part of it, I will say that it is an m-dimensional submanifold. M should be less than or equal to n, certainly the important case when this is less than n. Say 5-dimensional manifold, and I want to know what a 3-dimensional submanifold is. I can say again that in even different books, this notion is defined in different ways, very much not equivalent. So I want to consider some examples and to ask you, think about that, whether this deserves the illustrious name of a submanifold. First, I will not draw it. This probably will not give any problem. So take a plane, this table, and a line, straight line. It is a submanifold. Probably nobody will object. But we have not the whole line, only an interval. So whole plane and an interval in this plane. So some line, but not the whole line, but only a finite interval. Would you call it a submanifold? Or you think that it is something? You call it a submanifold? Yes. Yes. Yes, you're tolerant. Sufficient. No objections? Yes, it is common. It is a submanifold. Now suppose that we have a plane, this blackboard, yes, what else? Let me have some space. And a set of parallel lines. Y is 1. And so on. Actually, there will be two possibilities. Either we consider the line, limit line as a part of the set, or we don't. Let us begin with the case when we don't. So, just the union of this line. Would you consider it as a submanifold? You say yes, Henry, because it is actually not worse than a favorite interval. Yes, it is a manifold according to our definition. But if we take the closure of this, add the line y is 0, then it is not a submanifold, at least according to the definition which I am going to give. There are even still more radical examples. For example, take a torus. We have torus. This is product of two circles. And then, in the square of which this torus is made, take a family of parallel lines with irrational slope, tangent of the angle which formed by this line with the horizontal or vertical line is irrational. Of this line we can compose such a thing. we should take not all irrational lines, but just take enough these intervals so that we can have this, how to say, helix, it's not a helix, some winding, which is actually will be dense in the torus. And you probably will say that this is not a manifold. And I say that as usual happens to me. I agree and disagree. I agree because I will give now a definition that it will not be a submanifold. On the other hand, there are good domains in geometry where we have to consider this as a submanifold. And some of these fields in geometry are very beautiful, like, for example, if you ever heard of this, the foliation theory. So this is a submanifold dimension 1, according to this theory. Well, but after this short discussion, I want to give you a definition. So, we have X and we have Y. X is an n-dimensional manifold in the sense of our definition. It is called an m-dimensional submanifold of X if for every point Y, and Y which is also certainly a point of X, there exists a chart. X is a manifold, so it has charts. I consider maximal atlas. So when I say chart of a manifold, I just consider every chart which is compatible with all charts of some atlas. So maximal atlas. Charts are charts. There exists a chart which covers Y, so that the inverse image of Y is U intersection with Rm. I consider Rm as a part of Rn. Just for example, the m-dimensional plane spanned by the first m coordinate axis. So this is the definition. It is a submanifold. And this definition shows immediately that as this submanifold is a manifold. Because these charts the inverse of Y they form an atlas for Y, right? And now if we return to the examples which we considered, the thing which is not supposed here, we do not assume that Y is closed in topology of X. This is why part of our examples survive. This is true for points of Y, not for points of X. So points which do not belong to Y owe nothing to us. So this is submanifold. And you know, if submanifolds are manifolds, this gives you a lot of new manifolds. Let me say something else. After all, this condition may be geometrically, well, it is sort of clear, but still requires some clarification, being clear. Let me say to you something which you know very well again from calculus, which you teach in calculus rooms. I will begin with submanifolds of Rn. So we have Rn. It is X. And Y in Rn. And I suppose that every point of Y has a neighborhood in which y, so this is u, y intersection with u, is the set of solutions of a certain system of equations. Let me write x here. This equation should be non-degenerate in the sense that the Jacobian matrix of these functions with respect to the coordinates in xn, so dfi dxj, should have maximal rank. You can express this in 1,000,001 more ways. You can say that the gradient vectors of these functions are linearly independent at every point of y. This is a description of a certain subset of Rn. And I want to say two things. The first thing, that it is a submanifold of Rn. But what is more important, that it gives you an equivalent description of submanifolds of Rn. So why this is a submanifold? Why is this a submanifold? Look. So according to the definition of a submanifold, for every point y and y, and actually my definition involves some point y and y, for every point y and y, we should have a chart with certain properties, chart of Rn. Let me do the following. Consider y and y, this u as here, and the functions f1, f, and minus m. When I say that these functions form a non-degenerate system, that is, the Jacobian matrix has a maximal rank, then what do I mean precisely? I mean that there are coordinates n minus n of them, xi1, xi n minus m, that is the determinant of the Jacobian, dfi, maybe better to write k1, k, dx, kj. This is n minus m cross n minus n matrix. It has determinant. It's not equal to 0. So there are special coordinates for which it's not 0. Maybe this set is not unique, but it exists. Now we do the following. Take the rest of x's. xj1, xjm. The total amount of x is n minus m there, and m more, right? And just add them to this system of functions. So now we have n functions. Coordinates are functions, believe me. So we have n functions. What about the n functions of n variables? What about the Jacobian? It is very much not 0. Why? The Jacobian has the following form. Jacobian with respect to x's. First, this matrix is here, right? And then in m more columns, we have ones and zeros elsewhere. And it is clear that the determinant of this matrix up to a sign is equal to the determinant of this, right? So it is not equal to 0. Even if we have to change the sign, it's still not 0. And now in analysis, which maybe is not taught in calculus rooms, but still is taught in the undergraduate classes, there are theorems which I prefer to use without any restrictions. The first of theorems, chain of theorems, which I mean, is the so-called implicit function theorem. There is some, but I want to have theorem which is easy to formulate, although certainly it follows from the implicit function theorem, the inverse function theorem. If we have n functions of n variable, nick, and the Jacobian is at some point is not equal to 0, then there is a neighborhood of this point in which these n functions give a one-to-one invertible map of this neighborhood onto some set. N functions, excuse me, always give you a map of Rn into Rn, right? This map, we don't know much about it. But if at some point y, this n function have a non-zero determinant, then this map is invertible in some neighborhood of this point. Invertible, which means that this map is smooth and the inverse exists and also smooth. This is what the standard inverse function theorem says. If you have doubts, please not for me. There are textbooks in analysis, which probably you have in the bookshelves. Look, inverse function theorem. It is necessary to know these theorems like this if you want to consider manifolds. Now, this is all. Because what I say means these n functions form a chart in Rn. The inverse map forms a chart in Rn which covers y, which precisely satisfies the condition which is a part of the definition of a submanifold. So, the result, this is a submanifold of Rn at least. And we have many submanifolds in Rn. Again, when we return to calculus of the calculus room, you have certainly surface integrals, I don't know what. Sphere, your favorite example of the sphere. x1 squared plus so on plus xn squared minus 1 is 0. This is very much one equation, which, according to my construction, determines an n minus 1 dimensional manifold if it is in Rn. N-dimensional if you take this in Rn plus 1. But actually, any surface which you can sort of draw in space. You know, all the topologists love this a lot. Spheres with handles, I don't know what. Surfaces, created surfaces, all of them become manifolds. And in reality, this construction gives you all manifolds. I just want to make two small remarks about this. First, I consider submanifolds of Euclidean space. But it's also possible to consider submanifolds of any manifold in this way. Because if you have a manifold, then it doesn't have coordinates. It does have coordinates, but it does have local coordinates. And with respect to these local coordinates, again, we can consider equations like this. So precisely in the same way, with all the same, we can consider submanifolds in every manifold. And they locally are given by equations. Locally. Is it really necessary? Say sphere. One equation. The sum of the squares minus 1 is 0. What do you think about this? Maybe this locally is not necessary. For example, well, maybe we should consider, say, compact manifolds, or maybe just closed in the topology of Rn or any manifold. Maybe I don't need this nasty word locally. What's your impression? What seems plausible? For example, you have, say, in a 4-dimensional space, some 2-dimensional, some maybe very much compact, even actually homomorphic to a sphere. I don't mind. I prefer to have it given by 2 equations given globally, at least some neighborhood of the sphere, well, globally, but one system of equations. Do you think it is right? I just want to have your opinion, not any proof. What seems more plausible to you? This locally, simply we say this to be on the safe side, or it is really necessary? What seems more plausible to you?
It is necessary.
Who says that it is not necessary, that globally will be always okay? You all are too cautious, but you are right. But you are right, yes. Even there are examples of what I said, 2-dimensional submanifold of R4, which topologically is a sphere, but cannot be given by 2 global equations. If you are involved in some algebraic geometry, who of you is involved in algebraic geometry? Nobody. You. Then you may heard that there is such a thing as complete intersection. Algebraic geometry, they allow it. Precisely a submanifold which is given by a global system of equations. So the fact is that this assumption of being local is necessary. Now I want to use the remaining 1 minute and 22 seconds to say the following thing. Certainly we are not algebraists. We sort of feel that we are superior to algebraists. But still, if we want to go down to this level, and just imagine what algebraists would have said about this. And we said, well, you have manifolds. They should be objects of some category, say they. And so there should be also morphisms, maps. Well, this may sound nasty, but in this case, we have to admit that the algebraists are more right than wrong. So a map between one manifold into another manifold, which maps deserve to be considered as an item in differential topology. Which maps? And you say immediately, smooth maps. A map of x and y to manifolds. A map is smooth. If it is smooth, I don't have time today to write equations. Smooth with respect to local coordinates. So there are smooth maps. Smooth always means C infinity for us. I will make a small remark about it later, but not today. Now, so there are maps. If a map is invertible, then there is an inverse map, which also can be requested to be smooth. If the manifold x and y are connected by a bijective map, which has inverse, and both the map and the inverse map are smooth, then this map is called by a certain ugly word. Do you know the word? Just imagine the ugliest word you ever heard. Diffeomorphism. Diffeomorphism. Morphism is something generic like homomorphism, symplectomorphism, I don't know what else. Differ is clear. Diffeomorphism. A map of a manifold x into a manifold y, so it's smooth, inverse is smooth, and in this sense, if we are not algebraists, we can sort of think of diffeomorphic manifolds as of the same thing. So it's not different. Diffeomorphic. What is true for one is true for the other one. And then a theorem which I will eventually prove, but not today, because today actually I have only -1 minute remaining, not sufficient. The fact is that every manifold at all is diffeomorphic to some submanifold of an Euclidean space. In this sense, my example of submanifold Euclidean spaces is universal, gives everything. Thank you for your kind attention.